This video is an introduction to logarithmic expressions. This is AP Precalculus topic 2.9. If you appreciate this content, please give it a like. Every operation has exactly one inverse or opposite operation. We learn inverse operations because these will allow us to solve equations involving various operations. Because subtraction is the inverse operation for addition, we can solve an equation like this by subtracting 3 from both sides. Because division is the inverse operation of multiplication, we can solve this equation by dividing both sides by 3. Because the cube root operation is the inverse of cubing, we can solve this equation by taking the cube root of both sides. But what about exponentiation? 3 to the x power equals 7. How would we solve this? We need a new inverse operation. Just like we can write rational numbers in two ways, decimal form and fraction form, and they mean the same thing, we can write equations in two ways as well, which mean the same thing. We can write equations in exponential form, which looks like this, or logarithmic form, which looks like this. These are equivalent. We are not changing the problem when we change back and forth between these forms. This expression would be read, the log base b of c equals a. Example 1. Convert the following equations from exponential form to logarithmic form, or you can just say log form. Part A. Logarithms are the inverse operation of exponentiation. So you can undo exponentiation with a logarithm. If you take the log base 3 of both sides of this equation, the log base 3 and the base 3 cancel each other out, just like multiplication and division would cancel each other out. On the left side, that just leaves 2. And on the right side, now we have the log base 3 of 9. And this is log form. It has all the same information as the original equation, but this is considered log form, whereas the original equation was in exponential form. We can write part B in log form by taking the log base 10 of both sides of this equation. On the left side, the log base 10 and the base 10 will cancel each other out. That will leave behind x is equal to the log base 10 of y. Log base 10 is special. If the base of a log expression is 10, this is called the common logarithm, and it is traditional to write it without the base 10. For example, instead of writing the log base 10 of 10 to the x power equals the log base 10 of y, it's traditional to write log 10 to the x power equals log y, without showing the little base 10. That base 10 is still there, it's just understood. The same way when you write the square root, you don't put the little 2, but you still use it. So the invisible base 10 still cancels out the 10, and you still get x. For the final answer, it is traditional to write log y instead of writing log base 10 of y. But both are correct, and you will get credit for either answer. We can rewrite part C in log form by taking the log base r of both sides. The log base r and the base r will cancel each other out, leaving t on the left side. On the right side, we just have the log base r of w. We can rewrite part D in log form by taking the log base e of both sides of the equation. On the left side, we simply have log base e of y, but on the right side, the log base e and the base e cancel each other out, leaving behind 3x. So this is log form. Log base e is another special case called the natural log, and it is traditional to simply write natural log x instead of log base e of x. For example, this first line would be written natural log y equals natural log e to the 3x. the invisible e still cancels out this base e. So you would be left with the natural log of y is equal to 3x. By the way, the e is a constant like pi. It's approximately equal to 2.178. Example 2. Convert the following equations from logarithmic form to exponential form. Looking at part A, we can convert this log equation to exponential form by exponentiating both sides of the equation. In other words, you see the base 7 right here, log base 7? You can drop a big old base 7 on both sides of the equation like this, meaning on the left side we now have 7 to the log base 7 of x power. And on the right hand side we now have 7 squared. On the left side, the base 7 and the log base 7 cancel each other out. Again, this is just like multiplication and division cancel each other out. These are inverse operations. So we will just be left with x on the left. X is equal to 7 squared. Similarly, in part B, we can rewrite this by dropping a base 3 on both sides of the equation. This will leave us with 3 to the x power equals. The base 3 and the log base 3 cancel each other out, leaving the y. Part C. When you see the log with no visible base, we know it is an invisible 10. This is the common log we talked about before. So we can cancel out this log by dropping a base 10 on both sides of the equation. This base 10 cancels out the invisible log base 10, leaving behind y on the left hand side. So y equals 10 to the second power. In part D, this ln means natural log. That means there is an invisible base e here. So we can cancel this out by dropping a base e on both sides of this equation. The base e cancels out the invisible log base e, leaving c on the left. So c equals e to the fourth power. Now I will show you how to evaluate expressions involving logarithms. Sometimes we can evaluate log expressions without the use of a calculator by using its equivalent exponential form. Example 3. Evaluate the following expressions without a calculator. Part A. We can think of this as log base 2 of 8 is equal to n. And so if we find the value of n, then we have found the value of this expression. We have learned that we can get rid of the log by dropping a base 2 on both sides of this equation. The log base 2 and the base 2 cancel each other out, so that will leave behind 8 is equal to 2 to the n power. In this form, it's easier to see that 2 to the third power is equal to 8. That means n is 3, and n is the value of the whole thing. So really the answer is just the 3. We don't need the n. In fact, for simple problems like this, I don't want you to use the n at all. I want you to understand that the log base b of c is the exponent that turns b into c. A log is just an exponent. So this log expression is the exponent that turns 2 into 8. So because 2 to the third power is 8, log base 2 of 8 is 3. Let's try part B in this way. What exponent turns 5 into 25? That's 2. 5 to the second power is 25, so the answer is 2. What power turns 2 into 32? 2 to the fifth power is 32. So log base 2 of 32 is 5. By the way, if you did not already know that, you need to memorize that. Here are 12 facts you need to memorize in addition to your basic multiplication facts. So pause the screen, write these down, make some flashcards, and study them. For part D, remember that we have an invisible base 10 right here. So ask yourself, what power will turn 10 into 100? 2. 10 squared is 100. Did you know that the square root of n is the same thing as n to the 1/2 power? And the cube root of n is the same thing as n to the 1/3 power, and so on. Remember that when you ask yourself, what power will turn 16 into 4? The square root of 16 is 4. In other words, 16 to the 1/2 power is 4. So this log is equivalent to 1/2. Part F, what power will turn 3 into a 1? Well, anything to the 0 power is equal to 1, including 3 to the 0 power. For part G, don't forget about the invisible base 10 that's sitting right here. The question is, what power will turn 10 into 10? Well, 10 to the 1 power is equal to 10. I recommend showing our work on part H. So we are asking ourselves, what power will turn 6 into 1 over 36? In other words, 6 to what power? So yeah, I prefer a question mark. When back on part A, I did this with an n, and I said 2 to the n power is equal to 8, rather than introducing some variable that nobody asked us for. Let's just use a question mark. So 6 to what is equal to 1 over 36? If we find the question mark, that's the answer. Let's rewrite the 36 using the same base, 6. Of course, 36 is 6 squared. So the question becomes 6 to what power is equal to 1 over 6 squared? How can we write this without the fraction? So I have 6 to what power is equal to 1 over 6 squared is the same thing as 6 to the negative 2 power. In this form, it's easy to see that the question mark is negative 2. Don't write question mark equals negative 2, just put negative 2. It's very easy to evaluate log expressions using a calculator. The College Board will accept 3 decimal places, but students often will make a mistake when it comes to rounding, so we are going to use 4 decimal places and no rounding. Part A, log 9. There's the log button on your calculator, so just hit log 9 and enter. We will write 0.9542. How about log 6125? Log 6125. You can close the parentheses if you want to, but if there's nothing else coming, you don't have to. We will write 3.7871. Part C, there is no log base 2 button on the calculator, so how do I type in log base 2 of 10? Hit the math button. The logarithms are way at the bottom, so it's quicker to actually scroll up. Okay, go to this option and hit enter. So now we're ready to type. So the log base 2 of 10 would be typed in like this. 3.3219. Let's do that again for the log base 7 of 135. Hit that math button, go up until you get right here. Now we can type the log base 7 of 135. 2.5208. That's it for example 4. One useful purpose for logarithms is for dealing with exponential data, which can be very challenging to display graphically because values may start out small but then grow very quickly. So it's difficult to create a display that effectively shows the smaller values along with the extremely large values. For example, the population of English Americans in the region we now call the United States since 1620 has grown exponentially. The estimated population is shown below from 1620 to 1820, where t equals 0 represents the year 1620. The graph on the left shows the population using a normal scale on the vertical axis. Because the population expanded into the millions, the data points reflecting the years 1620 to 1700 are almost indistinguishable. See how close they are to 0? It would be difficult to notice any differences in the population during these beginning years. On the other hand, the graph on the right uses what's called a logarithmic scale, base 10, for the vertical axis. Using a logarithmic scale allows us to view all the data points relative to each other, and we can see significant differences even in those initial values. Example 5. The population data of English Americans in the current United States for the years 1840, 1860, and 1880 are given below. Plot these 3 additional data points on the graph above. 10 squared is 100, 10 to the 3rd power is 1,000, and 10 to the 4th power is 10,000. I'm wanting you to notice that the exponent tells you how many zeros are after the 1. That's why 10 to the 6th power is 1 million, 10 to the 7th power is 10 million, and 10 to the 8th power, which I had to add on, is 100 million. Notice that the 3 data points that we need to graph are all between 10 million and 100 million. So these 3 points will fall between 10 to the 7th power and 10 to the 8th power. Don't forget that the numbers on the x-axis represent the number of years since 1620. 1840 minus 1620 is 220. So the year 1840 corresponds to t equals 220 on the x-axis. Similarly, 1860 is t equals 240, and 1880 is t equals 260. The populations for each of these years would be graphed about here, here, and here. One common type of graph with a logarithmically scaled vertical axis includes grid lines as seen here. This type of coordinate grid is likely to appear on the AP Precalculus exam. Notice that this is the same scale used in the previous problem, where 10, 10 squared, and 10 to the 3rd power are spaced equally. On a logarithmically scaled y-axis, we start with 1, not 0, because this is really 1 to the 0 power. And then between 1 and 10, each one of these lines you are counting by 1. So this is 2, 3, 4, 5, 6, 7, 8, 9, and then we get to 10. As you pass 10, you begin counting by tens. So it goes 20, 30, 40, 50, 60, 70, 80, and 90. Then we get to 100. Of course, as you pass 100, you begin counting by hundreds. So next is 200, 300, 400, 500, 600, 700, 800, and 900. And then finally, you get to 1000. If we kept going, the next line we would start counting by thousands. Notice that on a logarithmically scaled y-axis, 5 is not in the middle of the interval. It is much closer to 10 than it is to 1. Similarly, 50 is much closer to 100, and 500 is a lot closer to 1000. Example 6. Plot the following points on the same coordinate plane above, starting with A at 1, 20. So here's 1, and 20 goes past 10, but after 10 we start counting by tens, so this next line will be 20. So this is the point 1, 20, which I will just label as A. 2, 300, so here is 2. 300 is going to be past 100, but after that we start counting by hundreds. So this is 200, and then the next line right here is 300. So this is our B. 3, 2. Well, here's 3, and right at the bottom, this is 1, not 0. So the next line right here is 2. So this is point C. Point D, 4, 15. Here's 4. 15 is past 10. The next line is at 20. So 15 is going to be somewhere in this interval. Is it going to be right in the middle? Because, 15, it ends with a 5, and 5 would be in the middle. No, we just discussed how the 5 is actually closer to the next line. So make sure you put your 15 closer to 20 than it is to 10. So this is D. And then point E, 5, 350. So here's 5, here is 100, and then 200, 300. Don't put 350 right in the middle, put it a little bit closer to 400. It's hard to see because it's so small. But this is point E. Let me emphasize this one more time because it is a common mistake. 15 should be graphed closer to 20 than to 10. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.